So, in our first week, we discussed vectors as our tools. Okay, we discussed units and symbols over here. We discussed vectors. We discussed motion in general. We talked about specifically velocity. And we talked about acceleration. And velocity, we said, was a vector. It had direction. And it was equal to distance divided by time. And sometimes it was equal to a change in distance divided by time. So that's a change in distance divided by time. And we also talked about a change in anything was really a v final minus v initial divided by time. Okay? We talked about acceleration. And that acceleration, oops, I made a mistake here. A change in distance divided by time. A change in distance, d final minus d initial, which is nothing more than the start, divided by time. And I said that acceleration was a change. This is where that goes. A change in velocity divided by time, which is a v final minus v initial divided by t. We also said that these formulas can be used in this kind of form. Let's see. I want to go to here. Need our... Yeah, let's use these. We said I told you to put these in your book. Okay, they kind of look like this. Okay, so far so good. I'm doing a pretty good job drawing these, I think. And we said that velocity was equal to distance divided by time, and we looked at how to use this. And that acceleration, okay, was equal to a change in velocity over time. We could use those like that. Okay, so let's talk about force. Now, force. We talked about balanced and unbalanced forces. We did some practice problems involving motion and force. And we started to talk about momentum. So let's go to a new page and let's talk about force. The first thing we did is we defined it. We said that force was a push or pull on an object. Now, we said that that was the definition, and there was one man who did an awful lot of work with forces, and his name was Sir Isaac Newton. And we called all the work he did on it his first, and we'll talk about, he had many laws, but his first 3 laws. And we said the first was really, well, was often called the law of inertia. Okay, inertia. Well, let's try to find that right here in a way that I like. I use it all the time. Inertia was the laziness of an object to change. to any change at all. And that's kind of what, that's the way Mr. Albert Einstein, that's the way he taught it. Inertia, he would say, is the laziness of an object to change, to create that mind picture that people would remember. And the first law that Newton wrote said that an object, and I'll let you finish this, an object in motion, how did he finish that? I hope you said an object in motion wants to stay in motion, and an object at rest wants to stay at rest. But the most important thing, I think, was at the end of it, we qualified it by saying, I better write it all down. I'm going to say an object. Matter of fact, what I'm going to do is I'm going to type it. An object in motion wants to stay in motion, and an object at rest wants to stay at rest. Unless acted upon by an outside, and I'll even add this, comma, unbalanced. Here it is, the biggie, force. Okay, that's what we said in class. That's what we said his first law was. And now let's describe what that means. You recall in class that I took a pin and I blew up a balloon, and I told you I was going to press that balloon just a little bit with that pointed tack. Oops, object. Just a little bit, okay? And I said I was going to keep that in contact with the balloon. I was just going to keep pushing, and if the balloon were smart, it would move away. And it did. Okay, so as long as there was a force applied to it, there was continual motion. Not only continual motion, but a certain kind of motion. It was acceleration. Okay? But his first law said that if it's staying still, it's going to stay still. If we have an object, whatever it is, if it's not moving and it is just sitting there, it's going to stay there. But if it's moving, how can I draw this as moving? Let's see. If it is moving, okay, it's going to stay moving forever and ever and ever. Okay, unless acted upon by an outside force. What's an outside force? Something that opposes the direction it's going. Okay, it'll keep moving forever and ever. If the force is in back, like this, let's put a force in back. Here comes a force, the vector. And I'm going to push that vector right on it a little, whoops, right on it a little bit right there. Okay, it's going to go faster. If, on the other hand, I take this force and I push this way, and again, these are all forces I'm talking about here. It's going to slow down. Now, this isn't an unbalanced force. Well, what do we mean by that? And I showed you tug of wars and so forth and so on, where I said if we have an object, okay, and we have folks pulling on it, there's one person, and he is pulling on this thing with a certain force, and if it goes back and there's another person, then it's pretty obvious this thing is going to move because these guys are pulling it. But if, and they're pulling it in this direction, okay, but if we add a person over here, then he is not going to be pulling that rope as fast as he did before. And if we add another person, everybody equal strength, then we know that this center knot of the rope in this tug of war is not going to move because we have a balanced force. We have a force of two people pulling this way, which gives us a certain force, and we have another force, these are the same size because they're both vectors, pulling this way of two people. It's going to put 2p over here. 2p over here, 2p over here, nothing happens. So if I were to take this ball and at the same time clone this, let me just, if I were to take that force and let's see, make another one. Let me do it this way. An equal and opposite force pushing this way on that ball, the ball wouldn't change. It would keep doing what it's doing. Okay? An object in motion wants to stay in motion. An object at rest wants to stay at rest unless acted upon by an unbalanced outside force. That was the first law. But the second said this. The second law said, Newton's second. I like to say he did it for his ma. All symbols, right? So M is what? Well, it's the first letter in mass. A is the first letter in acceleration. F is the first letter in force. These are measured in newtons in honor of Sir Isaac Newton. Mass is kilograms. Meters per second squared is for acceleration. And these are all the units on this side. Okay? So, let's see. This was an important formula, his second law. Now, I like it when it's set up like this. And I'm going to explain why. That A is equal to F over M. And don't forget our formula circle. A is equal to F over M. Now this says, and you know that anything divided by into 0 is 0. 0 divided by 10 equals 0. 0 divided by 100 equals 0. It makes no difference. Anything trying to divide into 0 is going to give you a 0. Well, what this said is that if the force on an object was 0, no matter how big the mass, this is a 0, not an O, the acceleration would be 0. Well, what this is saying is that in order to have something accelerate, you've got to have a force on it. It's got to be a force. There's got to be a force there.